Please welcome to the stage Andrea de Gouveia, APS April Meeting 2024 Chair.
Okay, can everybody hear me okay? Excellent. So it is my pleasure to introduce the public lecture for this year's APS April meeting. So I'm Andrea de Gouveia. I am the chair of DPF and also the chair of the program committee for this year's April meeting. So this year's public lecture speaker is my colleague, Shane Larson from Northwestern. He's also from the Center for Research in Astrophysics at Northwestern. And I will say just a couple of words. Shane is an amazing lecturer. He's a theorist who's been doing gravitational wave physics for a while. He's very excited about LISA, and I'm sure we're going to hear about that. We're also very lucky that Shane teaches at Northwestern as well. He's a very gifted teacher of first-year physics, and I've actually attended some of his lectures, and I can say that I've actually hit him with a sledgehammer a couple of times, and he can tell you about that if he has time. But he's going to be telling us about the shaking cosmos, observing the gravitational universe with LISA. So let's welcome Shane.
Okay, well, thank you, everyone. Thank you to the APS committee for the invitation. It's certainly a great honor to be here. It's always really great to be able to go and talk to people about things that are very near and dear to our heart. I do gravitational wave astronomy. I've been doing it my whole career. I've been working on the observatory that I'm going to tell you about tonight, called LISA, for the entire time that I've been a physicist. And we are at a pivotal moment in LISA's history right now. We were just adopted by the European Space Agency. That means they and NASA have signed the agreement and signed all the international treaties with the member states of ESA in the United States that says we're going to do LISA. So the scientific community is spinning up to get to work on all the things that need to be done to get in the air. The prime contractors are being selected, and construction and all of that stuff will begin in about 9 months or so. So that's all leading to launch in the early to mid 2030s. And so this is a very exciting time and an optimal time to tell you all about the work that we're doing. So tonight I'm going to tell you a little bit about gravitational waves for those of you who aren't in the biz. I will tell you a little bit about LISA, and then I'll give you some very broad strokes about the kind of science that we do. Invariably what will happen is we'll certainly take questions at the end, but there will be some question that will come to mind 2 weeks from now, 2 in the morning. My physics colleagues who are in the audience probably know your significant other doesn't want to talk about astrophysics at 2 in the morning. So if that happens to you, my email address is right there, s.larson@northwestern.edu. If you send me an email, I'll do my best to help you answer your questions, find something you can read, and learn a little bit more about it. My blog is there, rightscience.wordpress.com. That is a public-facing blog. There's a lot there about gravitational waves, about LISA, about all kinds of different things in astronomy. It's really there so my mom knows what I do. So hopefully you can find stuff there as well. Okay? So this is an artist representation of LISA that you see on the screen. And so we'll talk a little bit about that configuration as we go. But I want to back up first to traditional astronomy. And one of the most remarkable things about our society is we have evolved to the point where the things that we do as scientists, which we do as astronomers, we observe the universe, we collect data, we collect knowledge about places that no human ever has nor ever will be able to go visit. We've collected that information, we've distilled it down into the essential facts about the universe and what it means to us as a species, but then we've also distilled it down into an understanding that is meaningful to all the other people we share the planet with. And I can show images like the ones that you see on the screen, and they are almost uniformly recognized widely by a vast swath of people in our species, which is really a testament to our ability to communicate the information and the things that we do in astronomy and physics every day. And that is a very remarkable thing to me. And so the kinds of stuff that we're doing today in gravitational wave astronomy is kind of a new challenge to take the things that we're learning about the universe, that we're learning about the universe with gravity, and making it as accessible and understandable to the world as these kinds of images. Now, the images that you see here, all of us have kind of grown up during the space age. They have been delivered to us largely through the equipment of massive astrophysical observatories. These are some of them. There are plenty on the planet that aren't shown here. But all of these have, over the last century or so, gathered all the information that you and I regard as the foundational knowledge of astronomy. There's more to it than this. My physics colleagues who are here in the audience with us will have heard a talk this morning that laid out that we also use astroparticles. Those aren't shown here. But by and large, the bulk of the knowledge about astronomy has come from the use of telescopes. Now, some of these telescopes look like you expect telescopes to look. Some of them, you can see me down there in the lower corner. Some of us get to do this in the backyard as well. I'm an amateur as well as a professional astronomer. It's kind of a weird thing about my psyche. But the others are, some of them are on the ground, and then some of them are in space. And that is a necessity of the technology because of the limitations of observing the universe, not just with light that our bodies are sensitive to, but with other light that we know is generated by the physical phenomena in the universe. Things that physicists are used to thinking of as light, but don't necessarily get called light when you learn about them. Radio waves, X-rays, gamma rays, microwaves, all of those are different forms of light. And in the last century, we have developed technology that is capable of sensing the universe in all those myriad different ways. Of course, the reason we do that is we've learned that every object that we look at in the cosmos, every astrophysical phenomena that we're interested in, we can learn something new and different and complementary about it by studying it in all these different flavors of light that we have access to through the application of technology. This particular galaxy is a set of galaxies that are merging. You can see there the cores of the galaxies are very near each other and these very long tails that stretch out behind them. Those are trails of gas and stars that are being left behind that we call tidal tails. We will come back to the idea of colliding galaxies a little bit later. So what's the point here? The point is, in traditional astronomy, we're really thinking about the universe in the context of light. And light really tells us the stories of what atoms are doing. Astronomy has been a game of gathering light from the distant reaches of the cosmos and then trying to understand what the atoms that emitted that light are doing, and thus learning about, inferring what is going on in those different astrophysical environments, whether they're the surfaces or interiors of stars, whether they're nebulae where stars are being born, whether they're the atmospheres of exoplanets, whatever it may be, we've been using light and atoms to understand what those distant places in the universe are. Now, those of you who are armchair astronomers, and certainly those of you who are professional astronomers, know that not everything in the universe can be seen or observed with light. There are plenty of things in the universe that are very difficult to observe with light or simply don't emit light at all. They will be familiar to those of you who have paid any attention to astronomy, things like dim stars or dead stars, things like black holes, certainly things like dark matter, a substance that we've been studying for 100 years and know almost nothing about. All of these things are very difficult or impossible to study with light. We know about them because they affect the universe that does emit light, but they themselves are often very difficult to study. But there's a truth about these objects that lays the stage for the kind of astronomy that I work on, okay? And that's that all of these objects, together with all the things that we are familiar with that do emit light, move and change under the influence of gravity itself. Now, that's great if you're a physicist because you've spent a lot of time studying gravity and you kind of know what gravity's influence on the universe is. But if you're an astronomer and you think about gathering data from the far universe, it's a little bit of a conundrum because we ourselves don't have physiological senses that are built for observing gravity. Every kind of technology that we've used to study the universe so far has, in a very real way, been a bionic extension of some sense we already have. A telescope is mimicking what your eye already does. Sensing particles hitting something is what you're used to when the baseball misses your glove and hits you in the chest. Okay? But studying the influence of gravity on the universe, none of us has a gravity detector in our elbow. And so it took physicists a long, long time to figure out how to do this. The first person to think about it was Einstein, and it all started with special relativity when he posited, the postulate of relativity, that nothing can propagate faster than the speed of light. So if you imagine two objects going around each other, two massive objects, these are two black holes that are slowly spiraling together. As they move, they are changing the gravitational configuration of space around them. And the fact that they're moving and that configuration is changing means that that information has to travel through the universe. But what Einstein taught us is it travels through the universe at a finite speed, at the speed of light or slower. It happens to be the speed of light according to Einstein's theory of general relativity. So this image here is showing you the bright waves that you see there are those changing configurations in the gravitational field, the curvature of space and time, as we say in the biz, propagating slowly away from the two black holes as they move and slowly spiral together wherever they happen to be in space. Now, you see lots of movies about this, and this is the preferred one that I like to show. This is from my colleagues at the Goddard Space Flight Center. The reason I like this one, as opposed to the kind of ripples in the pond movie that you often see, is that this shows quite clearly that these gravitational waves propagate away from these two black holes in every single direction. And that's really valuable to us as astronomers, because it means no matter where I am in the universe with respect to these two massive objects that are moving around, I will, if I can develop the technology, have the opportunity to sense these gravitational waves as they pass by me. This is why it's a valuable thing for astronomy. It doesn't matter where we are, but we have to understand what the signal looks like. Okay? So, what do we do about the signal? We don't have a physiological sense. We don't have a gravitational wave detector in our elbow. It took physicists about 40 or 50 years to decide what they actually could measure, what that signal would look like. It was finally solved in 1957 at a conference in Chapel Hill, which we all call the Chapel Hill Conference. I'm sure there have been other conferences in Chapel Hill, but if you say the Chapel Hill Conference, everyone thinks you're talking about this one, where a colleague of ours named Felix Pirani taught us what we have to measure to sense these gravitational waves. Okay, I'll show you that in a moment, but the first thing I want to do is I want to audiolize some of our gravitational wave signals. This is a way for me to demonstrate to you that there's true astrophysical information about a source like this that we can discern. It's very easy for me to demonstrate it for you, so you can discern it sitting here in the audience. It's a little bit harder to teach computers how to do it, but that's the whole story of analyzing data. Okay? So what I'm going to do is I have two gravitational wave signals. Signals are just data. We can graph them. They'll look just like waves. And one of the magics of the modern era is when you have data and you stuff it out through the headphone jack of your iPhone, it turns it into sound that your ear can hear. Okay, so that's all I've done. And I have two signals here. These were actually generated by my colleague Scott Hughes. So these are two signals. They are both the exact same thing. They are a 10 solar mass black hole falling into a 10,000 solar mass black hole. These are objects which don't necessarily emit light themselves. We could sense light if they're affecting the things around them. But the gravitational wave signal itself is what I've turned into sound. The two sounds are different in the following way. The first sound is circular orbits slowly shrinking, quasi-circular as we say. The second sound is an elliptical orbit, an eccentric orbit as we say. I haven't changed anything else except the shape of the orbit. But you can hear the difference in the gravitational wave data, which is exactly the sort of thing that we look for as gravitational wave astronomers. Okay? So here's the first one. I think it started to play. Nope. I don't hear it. We tested it, but it sounds like we lost the audio for it. Let's try it again. Oh, you're going to have to get my performance of it. Okay. Is it there, team? I don't think so. Okay. And the second one? I don't think the second one's there either. Okay. Okay. Oh. Oh, well. I'm good. I can perform it. Okay, we're good. Okay, so what the first one sounds like, it's what we call in gravitational wave physics a chirp. Okay, so you have two black holes going around each other in a circular orbit. Okay, and the frequency of the sound that we turn that orbit into is related to how fast the black holes are moving in that orbit. Okay, and it will start out initially at some very low tone. Woo, right? As the gravitational waves carry energy and angular momentum for the physicists in the room away from the system, the orbit shrinks. And as orbits shrink, the objects begin to move faster. And so the frequency, the sound, the pitch of the sound goes up. And then eventually, as the black holes get closer and closer together, the gravitational interaction between them becomes stronger, and so that signal gets stronger and stronger and stronger, and so the sound gets louder, and then they merge, and it's over. So the whole sound is like 30 seconds long. I can't do that whole inner breathing thing that musicians do, so I can't do it for 30 seconds, but it'll go whoop, just like that. Okay? So what's different if I make the orbit circular, right? The volume of that sound, the strength of the signal, depends on how strong the interaction between the two black holes are. So in an elliptical orbit, when they're far apart from each other, the interaction's kind of weak. But then when they get close together, they make a close pass, the signal momentarily gets strong, and then it gets weak again. And then it gets strong and weak again, and strong and weak again. And so when I start playing that sound, it sounds like the car you had in college, right? It goes bump, 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 like your engine's knocking. So what do the gravitational waves do? They carry away energy, angular momentum as well for the physicists. And what that does is it tends to circularize the orbit. It takes that what was originally an elliptical orbit and makes it smaller. Okay? And so those bonks get closer and closer together until it sounds almost like the first sound that I would have played for you, and then eventually they chirp, and they merge, and the signal's over. So it'll be like bump, 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 just like the other one. Okay? And you can absolutely hear that, and that's the point. True astrophysical data is stored in the waveforms, and all kinds of other astrophysical data stored in there as well. I can change the masses of the black holes, and the sound will be different. I can change the spin of the black holes, and the sound will be different. And so our job as gravitational wave astronomers is to teach computers to do what your ear can do, extract all of that information directly from the gravitational wave data. Okay? Okay, and afterwards, if people want to hear the sounds, I have them on my phone, so I can play them for you. So, okay. They spin up all the time when I'm like driving on CarPlay, and my daughter's like, really, again? I'm like, it's the music of the cosmos, hun. So, okay. So, there's a whole bunch of these different kinds of signals. And in astronomy and physics, we like to arrange them in the context of the size of the waves that we're observing. So there's an electromagnetic spectrum that describes all the different kinds of light, but this is a gravitational wave spectrum, okay? So this is all the different types of gravitational waves that we can observe, okay? The number plotted here is called the frequency. The frequency is basically if I take some set amount of time, a second, how many waveforms pass by me in that second. But on top of that, 1 over that frequency number is the number that I care about as an astronomer. That's roughly speaking the time scale over which the masses that I'm talking about move around. How fast do the black holes orbit each other? How long does it take the star to fall into the supermassive black hole, whatever it may be? Okay? So when I'm thinking about the universe and does it emit gravitational waves, I'm thinking about that number that's on top. The bars there represent the parts of the spectrum that right now we have excellent technology at our disposal that we're working on and implementing to sense the universe in gravitational waves. If you've been paying attention, our LIGO colleagues with LIGO, Virgo, and Kagra have been slowly reporting events. They're up to 100 or so, and they're going to announce their new catalog here at this meeting for the last 8 years or so. Last summer, our colleagues in the pulsar timing part of the spectrum announced a big result about the detection of a background of gravitational waves from the total universe. And what I'm going to talk to you about is right here in the blue marked box there, what we call the millihertz band, which is where LISA and gravitational wave observatories in space will observe. So why all this effort to make technology, to make observatories that can observe across the whole spectrum? It's because when you put a whole bunch of physicists, astrophysicists like me in a room, we start to imagine all the possible things in the universe that could be measured with gravitational waves. And one of the most exciting things about this field is that there is no part of this spectrum where there isn't something that will be terribly interesting and useful and important for us as astronomers to observe. Okay, and in the millihertz band here, you can see there is a wide variety of different sources, both in terms of different types of physics and astrophysical phenomena, but also, as we'll see in a moment, there are tremendous numbers of sources here in the LISA band. Okay, they're always on, they are persistent, as we say, and so there will be a plethora of gravitational wave sources that we are able to observe the moment we turn the observatory on. Okay? So let me tell you about the observatory, and then we'll go back and we'll talk about some of that science. Okay? So the observatory is going to be in space. It is 3 individual spacecraft. Each one of them is going to be about 2 meters across, maybe 50 centimeters deep. The final design is being worked on. They are separated by 2.5 million kilometers. And what they do is they shine a laser beam back and forth from one spacecraft to the other. And our job as gravitational wave astronomers is to time how long it takes those laser beams to fly back and forth between the spacecraft. Okay? So I'll explain that to you in a moment. The spacecraft follow the Earth in its orbit. You'll see there the triangular constellation of LISA maintains its configuration and cartwheels around as it follows the Earth around the sun. This is a clever choice of orbits. Each of the individual spacecraft is actually on its own orbit around the sun. We've just chosen those orbits carefully such that the constellation maintains that triangular configuration. Okay, so this is a beautiful, those of you who are physicists, there's a great paper to derive this using junior level classical mechanics. So it's a very cool orbital system they've developed. Okay, so that's the constellation. What are we doing shining these lasers back and forth? So the thing that our friend Felix Pirani worked out at that Chapel Hill conference I mentioned is that the way to measure gravitational waves is to understand what they do to the universe around them. So imagine that each one of those dots is a little bit of mass, a ball, a rock, something. Okay, and I've arranged them in a grid. And then imagine there's a gravitational wave source behind the screen, emitting gravitational waves that come flying through the screen and washing across the room where all of you are sitting. What Pirani showed us is that what the gravitational waves do is they change the proper space-time distance between each of the rocks in that grid of masses. And they do it in a very regular pattern. Okay, so this first one on the left, you'll see there are 2 axes. One is vertical and one is horizontal. And when the distance between the masses are stretched along the vertical axis, they're compressed along the horizontal axis. And then a little while later, they get stretched along the horizontal axis, and they get compressed along the vertical axis. Okay, so if you imagine drawing those axes, it looks like a mathematical plus. So we call these plus polarized gravitational waves. Okay? There is another flavor of gravitational waves that also distort the grid of particles, but along a different set of axes. Okay, and so here you can see that, and in that case, the axes are diagonal. They go from the upper left to the lower right, and from the upper right down to the lower left. And when they're stretching outward along one diagonal axis, they're compressing along the other, and then they switch places again. And so this looks like a big X. And those of you who remember your calculus class in high school or in college, that's called cross, okay, mathematical cross operations. So these are usually called cross-polarized gravitational waves. Okay, so this is the effect on the universe. And so our job then, once Felix realized this, is to then figure out how do we actually build some technology to measure this. There are many different ways of doing this. There are lots of different technologies we've tried, but the modern technology is to use laser interferometers. So you just imagine picking 3 of those masses in the grid. Those represent the mirrors in a laser interferometer that I bounce laser beams back and forth between. And so as the gravitational waves distort, the positions of those individual masses, the mirrors in my interferometer, I can see that happening because the lasers take longer or shorter amounts of time to get back and forth between the 3 corners. And that's the whole game. Okay? I won't tell you the numbers. They're scary. They're small. It's exquisite technology. Okay? But Einstein didn't think we'd be able to do this. He could compute how big the effect that I just told you about was. And he's like, no, there's no way this is ever going to be able to be done. But you and I live in the future, and we can do it. And our colleagues who are good at this technology, they've demonstrated it. We've successfully done it on the ground. We've demonstrated it in space. And in 10 years, we're going to build one just like this triangle, and we're going to do it in space. Okay? NASA and ESA don't let you do this unless you can prove that you can do it. So in 2015, we launched a mission called LISA Pathfinder. Okay, so this is the rocket launch and the LISA Pathfinder spacecraft down there in the bottom. The basic idea of LISA Pathfinder was to prove that we could monitor very accurately the position of 2 mirrors in space. We didn't do it over 2.5 million kilometers. We did it over like 30 centimeters. Okay, so we couldn't detect gravitational waves, but we could show that the technology worked. Okay, it worked beautifully. My physics colleagues in the audience will know that we have to demonstrate to the certain level for NASA and ESA to do it. We met the requirements that LISA needs. There's like no improvements we need to make. So we absolutely know we can do this. This is what our mirrors look like. Okay, they're made out of gold and platinum alloy. Okay, they're very shiny, so they can reflect the laser light. Okay, it's about 4 centimeters to a side, and it weighs about 4 kilos. Okay, now they don't let people like me touch things like this. Okay, because I get fingerprints on it and I lick it and things that are bad. So they made analogs of these. Okay, and so you can see there in my hand on the bottom, right? That is a 1-to-1 scale analog of the proof mass made out of tungsten, because tungsten has the same density, almost 98%, of the gold and platinum alloy in the mirror that's floating there on the top. So when you hold that tungsten cube in your hand, it's like holding the real heart of LISA. So we went to a meeting at Goddard, and they had 3 of these. They were handing them around. They were awesome. And I was like, I am going to go give a public lecture. Can I take this? And they're like, sure, you can take it. Just bring it back. So next time I was at Goddard, I brought it back, and they're like, what have you been doing with our cube? I'm like, I've handed this to 3,000 people. And they're like, okay, you just keep the cube. Okay? So I have the cube with me. Do you all want to touch it? Yeah, you do. Okay. So I'm going to pass the cube around. My only rule, those of the physicists in the audience will know this, tungsten is very dense. Okay, so it's not the easiest thing in the world to be safe with if you're balancing it on your head, whatever. Okay, but if you do take a selfie with it, please send it to me. I have a gigantic folder of selfies with the cube. I would love to add you to my collection. Okay? Okay, so I'll pass this around. It'll end up in the back somewhere. Someone please make sure I get it. And be careful. So that's the cube. That is the heart of LISA. That is what we're going to monitor when we bounce lasers off of it. Gravity will push it around, it will change its distance relative to the cube on the other spacecraft, and then we can measure that. Okay? So, that's the observatory. Okay, 10 years, we'll be in space, we'll talk about this again. We already are observing gravitational waves. We have other observatories. We have our pulsar timing friends. We have LIGO, Virgo, and Kagra, which have been making tremendous discoveries. What's the difference between all of these? The instruments are different, the technology is different, but why do we have the different instruments? So let me just do the comparison with LIGO, Virgo, and Kagra. If I think about the astrophysics, the objects that I can learn about with a terrestrial gravitational wave detector, I'm thinking about things that are moving very, very fast on very short time scales. That usually means they have to be very, very small, because the moment they touch, they become one object and stop emitting gravitational waves. Okay? But small systems, so they're very compact and they move very fast. Okay? By contrast, LISA sees big systems, and big in two senses of the word. We see much more massive systems, as we'll tell you about, but we also see systems that have much bigger orbits. They're moving slower than the objects that our colleagues who work on the ground actually see. Okay? So these are the different kinds of astrophysics. Some of the astrophysics overlaps between the two detectors. It would be awesome once LISA flies if there are sources we can study with LISA and sources we can study with our pulsar timing friends and sources we can study with LIGO. The universe, like people, ages, objects evolve and change over the course of their lives, and this kind of broad coverage of the gravitational spectrum gives us the ability to imagine that that's the kind of science we can do. So it could be very exciting. We'll see how it goes. But let me take this in mind then, and let me tell you the three main big sources that we're going to observe with LISA. There's a tremendous amount of astrophysical science that we can do with LISA. We've written massive 1,000-page review papers about this. But let me just give you a flavor of some of the things that we're going to study to help you kind of understand the scope of all the things that we plan on doing. Okay? So one of the things you may be aware of is that at the center of most galaxies, there is a massive black hole. Okay, there is one at the heart of our own galaxy. It's called Sagittarius A star. There are many lines of evidence by which we know it's there. But one of those lines of evidence, this is a movie from our colleagues at UCLA, is we can see stars moving around some intense source of gravity in the center of the Milky Way that is not emitting any light. If I study the sizes of those orbits and the speed that the stars are moving, I can measure the mass of that dark, unseen object. It is about 4 million times the mass of the sun. Okay? We think this happens in the center of most galaxies. One of the kind of truths of modern astronomy that's happened just in my career since I started is that most galaxies with big, bulgy centers, like the Milky Way, have a big black hole just like this. And so consequently, they have clusters of stars, just like this. And it begs the question, how often might stars fall into that black hole? And the answer is not often for one galaxy, but pretty often across the whole universe. And so one of the things we are going to look for is something we call an extreme mass ratio inspiral, an EMRI. We imagine that if there are stars in the center of the galaxy, sometimes they will die before they fall into the black hole. They will supernova and become a black hole or a neutron star, and over the course of their life, they will eventually spiral into the black hole. And during the late stages of that inspiral, they will execute these extreme orbits that you see on the screen here. We will sense these gravitational waves from these orbits with LISA. And in a very similar way to what we call satellite geodesy in physics, if we study those orbits, it tells us something about the underlying gravitational structure of the black hole. It allows us to study whether or not the black holes are exactly the black holes that Einstein and general relativity predict. So, That's kind of the gravity side of it. But also, depending on how often this happens, it teaches us how often does the black hole suck up and eat all of those stars that are around it in the center of the galaxy, which is part of its diet that tells us something about the history about how these big black holes grow. Okay, so there's a tremendous amount of astrophysical science related to these. Now, I mentioned earlier these colliding galaxies. So galaxies do collide. We see lots of evidence of this. And when they do, they merge to form a new single galaxy. But I just told you all of these galaxies have big black holes at their centers. So when they merge, what happens to their big black holes? Well, it's just like when you put heavy rocks together in a bowl of popcorn and you shake it around, they sink to the bottom. Okay, and so the big black holes in all of these merging galaxies, when they merge to form some new single galaxy, the big black holes will eventually sink to the center, and when they find each other, they will move around each other slowly over time. They will emit gravitational waves that LISA is sensitive to, also our pulsar timing colleagues. This is the thing they think they're seeing as well. And then they will eventually merge. So we will see perhaps 10 of these a year, perhaps 10,000 of these a year. We don't know, because it's a great mystery still in modern astrophysics about how big black holes grow to the size they are. We get those numbers that I just told you, 10 to 10,000, by looking at how often galaxies merge. But that doesn't tell us the whole story. And so we need this new way of sensing the black holes directly with LISA in order to answer that question. Okay, so this is, if you hear other talks about LISA, this is the thing you'll hear a lot about. People are really excited about this prospect. I should also note, as you can see here in this movie, these black holes, as they are getting close to each other, they are kind of sucking up gas and dust from the galaxy. That means there should be signals, light, that we can see from these black holes that we can observe with telescopes. So this is a prime, what we call in gravitational wave astronomy, multi-messenger source. There should be both things we can see with telescopes as well as things we can see with LISA. And if we can do that simultaneously, then there will be a tremendous amount of black hole science that we'll be able to uncover. Okay? The last thing I want to tell you about is actually what my group works on the most. We work on the Milky Way galaxy itself. One of the things you may remember from when you first took astronomy class is that in the galaxy, roughly half of all the stars you see live in binaries. Okay, that means just like planets go around a star, the two stars can orbit each other. When those stars die, their skeletons that are left behind, white dwarfs, neutron stars, black holes, will orbit each other very, very rapidly, and they will be prime sources of gravitational waves for LISA. The estimate is in the Milky Way galaxy, there will be between 10 and 50 million of these ultra-compact binaries that will emit gravitational waves that we should be sensitive to. Okay? Now, there's a problem with that, because if there are 10 million sources of gravitational waves going off at the same time, how do we discern which ones we're talking about? So the way we describe it, actually I'll describe it in terms of the conference, right? Earlier this afternoon we had a big coffee break and we were all out in the hallway right there, okay? And everyone was talking at exactly the same time. And so all you could hear was all this hubbub of conversation. They're all roughly the same volume, they're all roughly the same frequency, they're all roughly the same signal, they're all words, okay? But you couldn't discern all of them. You could discern some of them. You could discern the really loud people, and you could discern the people that were close to you. But the background hum was always there. So it will be the same thing with the galaxy. Out of the 10 million stars, there will be some 30,000 or so that we will be able to individually pull out of the gravitational wave signal of the galaxy. Okay? And from those 30,000, also from the 10 million that we can't separate, we will learn about the stellar evolutionary history of the Milky Way's graveyard, which is cool. Okay? So this is a movie of one of our models from my colleague Tyson Littenberg. It is flying outward from the sun, okay, the big yellow spot. And as you see stars appear, each of these individual stars is one of those 30,000 resolved individual sources. What you will see is you can see the entire shape of the galaxy is revealed. We can see these across the entire Milky Way galaxy. You will see some big black dots. Those are ultra-compact white dwarf binaries that we can already see. We can measure their orbits and predict how strong the signal will be for LISA. There's a group of purple ones. All the purple ones are ones that are easily accessible with an electromagnetic telescope. All the red ones are the ones that we can only see in gravitational waves. But in that purple group, there could be as many as 10,000, depending on how big a telescope we want to throw at it. So LISA is truly going to be a multi-messenger machine. We will have more telescopic access with light and gravitational waves to any gravitational wave sources of any observatory that exists today. So this is really going to be the game for LISA. Okay? So those are the three main source classes. The thing that's different about LISA is there's no waiting around for all of these signals. They are on all the time. There are events like the chirps, which happen, but prior to the chirp, the signals are strong and detectable, and we will sense them in the observatory. Okay, and I don't know if we fixed the sound, but I have another sound here from my colleagues at the AEI, where they have simulated a year of LISA data and put all the binaries and all the emeries and all the black holes together as one audio file. Okay, so if the sound works, I'll play it, but if it's not, then I'm happy to play it for people afterwards if folks want to come chat with me. Okay, so let's see how it goes. Nope, we lost it. Okay. So anyways, but you can hear, it's awesome, right? It's just like we were talking about the cocktail party, the coffee break problem, is you can hear all of the noise, but then you'll hear those chirps on top of it, right? And you'll hear the emery spiraling in on top of it. You can separate these signals out, even though they're all going on at the same time, just like you do in everyday conversation. Okay? Okay, so what do I want to leave you with? The first thing is, you know, I've been doing this my whole career, ever since I was a graduate student, and certainly the whole time as I'm a professor. I do this with lots of my colleagues. There are 1,500 scientists around the world that work on LISA, but I do it largely with my students. And so when I'm a 99-year-old and, you know, I'm in the old physicist's home and you're smuggling tacos and Legos into me, you know, these are the folks who are going to be doing the work that I'm doing right now. Some of them are at this meeting, so if you see them, chat them up, ask them what their favorite thing about LISA is. But these are really the future of this astronomy. I grew up in an era where we are transitioning from not having gravitational wave data to having gravitational wave data. They will never work in astronomy in a time when they don't have gravitational wave data at their disposal. This will be as common and as useful to them as ordinary telescopic data is to me and my astronomy colleagues now. Okay? And that's a remarkable paradigm shift for the discipline. Okay? There are, of course, plenty of other people. This is a smorgasbord of pictures from both LISA and LIGO. There are thousands of astronomers and physicists and engineers around the world who work on this, but it really is more than this, right? Behind all of us who do this work and all of us who get to stand up here in front and talk to you, all of us who get on the news and get to tell you about these awesome results, there are thousands of folks who don't have jobs as physicists who are supporting us. We have welders who put the instruments together for us. We have truck drivers who truck liquid nitrogen across the planet. There are titanium miners. There are rocket designers. There are IT professionals. There are secretaries. There are literally 10,000 other people who make the story that I just told you possible. And the legacy of everything that we do in gravitational wave astronomy, it's part of what we leave behind as astronomers, but it's a legacy that all of you who have your own professional careers also are involved in and own. The things that we're discovering about the universe and our place within it is a story that we are figuring out, but we're sharing it with everyone else because it matters for us as a species, us as our civilization, us as a society, about the things that inspire us, the things that make us get out of bed every morning, the things that help us find meaning about our place in the universe, and the things that matter to us. And I think the thing that's most important about this is when we demonstrate that we can do something as complicated and figure out something as hard as gravitational wave astronomy, it really should encourage you to believe that all the challenges that we face as a species on this planet, we can resolve. Because these are not easy problems to solve, and if we can solve these, we can really solve any problem there is. And that's the real legacy that we're leaving behind from projects like this as we do this science every day. Okay? So, I never like to end without leaving you some other things to read. So, here's a few books. They are not all of them completely about gravitational waves. Some of them are. Kip's book in particular is about lots of different things in gravity, but includes a bit about gravitational waves. Lots of them are very LIGO-centric because they've been written in the last few years during the era right after the first discovery, but they often will mention LISA and tell you about what the future will entail. Okay? Once LISA flies, I promise I'll write a public level science book about LISA, and then you can read that one too. Okay? Links there as well to various websites about LISA that you can certainly look things up on. And I am going to end there and say thank you so much for your attention, and I'm happy to take some questions.
All right, so thank you for this really amazing talk. We have time for questions and comments from the audience. And we also have people online. If you have any questions online, you can type them up and we'll try to collect those as well. And just like with the other talks, if you have a question, you can walk up to a microphone and let us know what the question is. So, Hamish.
Thank you so much for this wonderful talk. I was very interested in the grid pattern of the gravitational wave effects. And I always had a question, which is I'm sure it's a naive question, but my understanding of what gravitational waves are really a distortion in space-time. Mm-hmm. And so the distance between the mass points is different because actual space and time has changed between those points.
Yeah.
So if that's true, and I put lasers on those 2 points, why doesn't the light speed also change?
Yeah, so that's a great question. So there's kind of a detailed technical answer to that. Are you a physicist?
Yeah.
Yeah, okay. So if we derive gravitational waves from general relativity, we work in the linearized limit. And in the linearized limit, when you look at the distortions of space and time, what you find is the distortions confine themselves to the spatial sector. There is no distortion to time. If we go to the fully nonlinear limit, and there's plenty of colleagues here probably who work in general relativity, then you do have to worry about the time distortion as well. In terms of the propagation speed of gravitational waves, if you were at the talk this morning, this is something we try and measure because relativity predicts everything should propagate at the speed of light. And so that is something that we can measure, and that's part of this kind of distortion of time and space together that you have to work out and consider when you make that measurement.
So there would be a bandwidth limitation or something that would come out of that. Is that correct?
Okay, so bandwidth is a word we use for a lot of different things, but there is a band which we're sensitive to, which is basically defined by the time of flight between the two masses.
Yeah.
Yeah, that's right, absolutely. Yeah.
Thank you.
Okay.
So there's a question there.
So you mentioned the background hum, and my question was, because of that, is there like still a use for less sensitive, like maybe older detectors in measuring like larger events without that?
Yeah, that's a great question. Yeah. So anytime you build an observatory, an instrument of any kind, right, you're always going to ask what's the capabilities, what's the grasp. And so we always endeavor to build the best detector we can. And LISA's absolutely the first of its kind. Right? So there is nothing that we've done before that works at these frequencies where LISA is going to observe. Now, we have asked the question, what if we didn't make it quite as good as we're planning to make it? And usually the reason we ask that question is, can we save some money when we build it? Okay, and the answer is lots of the money that goes into this isn't going into making it as sensitive as we think it's going to be. If we made it less sensitive, we'd spend almost the same amount of money. So we'll get the science gain if we do that. Okay. Now, there are other parts of that question that are important, which is suppose we could develop another technology that would work at these same frequencies. And I'm a big proponent of the idea that we should absolutely build that technology as well. Because anytime you're working in this kind of new area of physics, you don't know what you're going to find, and you don't necessarily know that you understand everything well enough. And having multiple observing techniques, particularly in astronomy, is valuable because it helps you isolate what we do and don't understand, what we call systematic errors in the game between the different measurements. So if there were some other technology that we could use in this band, I would be all for adding it to the mix. So.
Thank you.
Okay, that's a great question. Thank you.
Thanks for this nice talk. I have a question. So I assume lasers are used to measure distance between 3 satellites. But I imagine that this distance is also affected by other objects in solar system.
Yeah.
We found objects in solar system by observing planets and changes in the orbit. How do you correct with effects of gravitational field in the solar system?
Yeah. That's a great question. Yeah, so that triangle, even though I draw it and I treat it as rigid, it is not. So the distance between the spacecraft will change by about, 2.5%, 5% over the course of a year. Those changes are slow, so they don't happen at the same time scales that we're trying to measure gravitational waves on, to the bandwidth question that was earlier. But it means traditional interferometry, the way you and I think about it, is not possible. Okay? In fact, the traditional interferometry isn't possible because I only send out a watt of laser power, and I get 1/1,000,000th of a watt at the far end. So I can't reflect it off a mirror and send it back. So what I do is I monitor the phase at both ends, and then I transmit all that phase down to the ground. I hand it to a graduate student, and they digitally create the interferometry signal. And so we have a specialized interferometry technique called time delay interferometry, where we account for the distances. And it was you can mathematically show it works, but we have to prove it works. And so our colleagues at the University of Florida in particular, colleagues in Australia as well, I think, have done this in the lab with, kilometers of optical fiber to show that this kind of time delay interferometry works, and it appears that it will. So.
Okay, very cool. Thank you.
Great question. So.
Yeah.
Hi, yes, thank you for the talk. Curtis, assistant professor at San Jose State, and hoping you could talk more about possible cosmological applications. Could it tell us about theories of inflation or something else about cosmology?
Yeah, no, that's a great question. So we have a whole cosmology working group. They worry about all sorts of things, exotic things, cosmic string networks, all of that stuff that you hear about. I think the most kind of direct and important cosmology thing will be from the supermassive black holes. Not only will they tell us something astrophysically about the history of the growth of supermassive black holes, but gravitational waves, especially of these sources, give us a completely independent way of measuring distances across the universe. So this was something that was worked out by a colleague of ours, Bernie Schutz, in the 1980s, and it will be in full force when we measure these gravitational waves from the massive black holes. So we'll have kind of precise non-electromagnetic measurements of distances on cosmological scales. And with all the debate about dark energy and the expansion of the universe, that I think is probably going to be the most prominent cosmological impact initially. So, okay,
There's one more question.
One more question, okay.
Okay, look at me. Thanks very much.
Yeah.
I'm Declan Mulhall from the University of Scranton. You mentioned something at the end that set me thinking about these large projects that involve thousands of people. You said that you mentioned the truck drivers, the caterers, the welders, and it was all very heartwarming and all the rest of it. But then I'm thinking, in projects like these, there's publicly spoken aspirations that these projects make us better and all the rest of it. But then you could find that under the hood, there's some supply chain horrors, right?
Yeah.
So the LISA project, you're familiar with this. When I'm thinking about these projects, maybe it's LISA, maybe it's LIGO, CERN, IceCube, any of these big projects, is there how would it work if you were to notice that in order to make this project work, it's contingent on some, like I said, supply chain horror. Maybe the people in the catering company are being exploited. Maybe the cleaners in the dorm rooms are just being treated horribly or something like that. So these are the things we try and we're better than this.
Yeah.
How does it actually work in these big projects if you were to notice some horrible stuff going on? Is there a coherent process or a policy that's actually implemented? Or is it just people being aspirational?
No, I think that's a great question. I think it's one that all of us engaged in this endeavor have to think about, right? So much like our professional societies, we are learning as a big collaboration how to deal with our interface with society and be better than we are before. That applies certainly on the internal workings of our collaboration. How are we more inclusive? How can we be more equitable in our work? But it also applies to our interface with the outside world. And I think, one of the difficulties that we have as scientists in particular is that all of us are embedded in much larger institutional organizations, which are responsible for those kinds of interfaces. And so it becomes incumbent upon us to influence those organizations we are a part of so that they become better as well. Okay, now is there actual things in place? For a big international collaboration like LISA, one of the things we have to struggle with is the way we think about things here in the United States are not the same way our colleagues in Italy think about things, right? We will approach problems like this in a way that our Italian colleagues, their laws and their cultural norms don't allow them to respond in the same way. And so we have to navigate as a collaboration how to deal with that as well, right? So it's hard. But I will say there's a great story from our colleagues at LIGO about the power that we as scientists have to build that interface better. And that has to do with when they were building LIGO the very first time. So the LIGO arms are gigantic 1 meter spiral welded steel tubes. It's the largest vacuum system in the world. It was built by the Chicago Bridge and Iron Works from my neck of the woods, and they on site built the welders, welded them on site. And so the story goes that when they were doing this, the welders one day threw down their welding torches and they said, "We are not going to weld 1 more inch of this thing unless you tell us what the hell this thing is for." Okay, now it just so happened that Ray Weiss was at the site that day. Ray won the Nobel Prize for the discovery, as many of you may know. And he, right, has this ethical sense, I think, that you and I are talking about right now. And he threw down what he was doing. There's a famous picture of all the welders there, their helmets and their welding chaps. And Ray, on a big piece of folding paper, taught them what I just taught you about how gravitational waves worked. Because he felt, as many of us do, that it's just as important that they're invested in this as we are, because I can't do it without them. So I think that really is, I think, the best answer, or maybe the only real answer I can give you, is that it sits with all of us, and it's incumbent on us to make sure it sits with those above us, right? Okay. Thanks for the question.
On that note, I think we should thank Shane again.
Thanks, everyone.
And I'll see everybody who's in the conference tomorrow morning at 8:30 or something like that.
Early in the